Okay, the motivation for derivatives is to understand the slope of the tangent line. So I'll start from there. We also use this as a motivation for limits. Okay, so now derivatives as slopes. So the usual setup is the following. So let's invent something like this. So this is y equals f of x. We have a curve. We want to understand the slope of the tangent at this point, say x sub 0. Okay? So let's draw a line from here. So you see it is difficult to draw the tangent line here, which exactly touches it. So we draw a second line, and then move this second line down until it becomes tangent here. What will be the witness for this to be a tangent? We have this point here. Okay, so instead of mechanically thinking of moving this down, we'll order this point to move along the curve until it meets this point. Okay, and then at each step in between, we will calculate the slope of this second line. And when this point meets this point, the slope, the resulting slope, we will agree that it is the slope of the tangent line. So you see we are talking about the limit here, when this point goes to here. So when we do that, okay, so let me do it this way. So we moved from x sub 0 a little bit to the right, or maybe to the left. Okay, so in this picture, delta x is positive, but delta x is meant to mean difference in x. Okay, so d in difference and d of delta are expected to remind you the same thing. Okay, so in general, we allow delta x to be a small value, positive or negative. In this picture, it is positive, but we could draw the same thing on this side. Okay, so we calculate the slope of this, and we take the limit of the slope as delta x goes to 0. Okay, so that is the position. So let's draw something like this here. So what is the slope of this? This distance divided by this distance. In order to find this, we have to check the coordinates. So the coordinate of this point is x sub 0 evaluated with f. So this is f of x sub 0. Okay? And the coordinate of this thing is, x coordinate is this time, x sub 0 plus delta x. And f is evaluated at that point. So it is this coordinate, f of x sub 0 plus delta x. Okay. So we will also need this auxiliary point. X coordinate is this point, x sub 0 plus delta x. And the height is this height. Okay, so that is f of x sub 0. Okay, now we have to look at the distances. Okay, so let's invent another thing. So this distance here, okay, so this distance is what? This subtracted this. Okay, so this is f of x sub 0 plus delta x minus f of x sub 0. Okay, so I don't have this. So this is the length of this. And I look at also the length of this. Okay, so it is this point minus this point. So that is delta x. Okay. If I did this picture on this side, then signs will change on this part and on this part. So, but after you cancel the sign, you'll get the same slope. Okay, so from here we say, okay, therefore the slope, hence the slope of this second line is this length, f of x sub 0 plus delta x minus f of x sub 0 divided by this length, which is just delta x. Okay. Now we agree that if this quotient has a limit as delta x goes to 0, then that number will be assigned as the slope of the tangent to the curve at this point. Okay, so let me write this because that's the geometric interpretation. Okay. Okay, so we agree that if this slope has a limit as delta x goes to 0, okay, the limit will be assigned as the slope of the tangent to the curve y equals f of x at x sub 0. Okay, so that's our agreement. Then we take this limit. So let m equals limit as delta x goes to 0 f of x sub 0 plus delta x minus f of x sub 0 divided by delta x. So assume that the limit exists. We assign it the number m. Okay. We denote this since for different functions we will obtain different limits. Instead of calling them all m, we want to show that this m depends on f. We call it the derivative of f at x sub 0. Okay. So we call m the derivative of f at x sub 0 and denote it by f prime x sub 0. Okay. Okay, now that we assume the limit exists, the answer to the original question is what is the equation of the tangent line to the curve at that point. Finally, well, we say but you can multiply. You always want to make this difference. You can multiply both sides of the equation by the same number. You can change the places of the terms in the equation, so there's no the equation, but sometimes we say the anyway. Finally, an equation for the tangent line to y equals f of x at x sub 0 is, okay, so first of all, it passes through the point x sub 0, f of x sub 0. So it is y minus f of x sub 0 is equal to slope times x minus x sub 0. Okay, but this slope is equal to f prime x sub 0. Okay, so in shortcut, we write y equals f prime x sub 0 times x minus x sub 0 plus f of x sub 0. Okay, so you can simplify this, change places, but this is the equation of a straight line. It passes through the point x sub 0, f of x sub 0, and it has a slope which we obtained by looking at the limits of the slopes of general seconds. Okay, so this is going to be one of the major achievements of calculus, because it was this question that one of the questions that were of interest was to understand the meaning of tangent. Okay, so of course, now after the invention of calculus, for hundreds of years you work on this, and now it looks very simple. Why did it take thousands of years for humankind to think of this? But you see, there are other things you filter out the details, and now you just present the correct question, and the answer is obvious. But it takes centuries to formulate the correct question. Okay, so let's check that this actually works. Okay, so let's look at slopes of certain things. Let's start with the obvious one. Okay, we'll use this. Okay. Okay, so let's calculate some examples. Okay, so suppose f of x is equal to 1. Okay, so the graph is something like this. Okay, so this is the graph. This is y equals f of x, which is equal to 1. Okay, so it's already a straight line. So we expect the tangent line be itself. So at any point, the equation of the tangent line must be y equals 1. Okay, so let's check if these calculations will give that. So let's say we have x sub 0 here. So this point is x sub 0, 1. F of x sub 0 is 1. Okay, so we have to calculate the derivative. Okay, so f prime at x sub 0 is equal to limit delta x goes to 0 of, okay, so let me write this, f of x sub 0 plus delta x minus f of x sub 0 divided by delta x. Okay, now I substitute these. First, limit delta x goes to 0. This is 1. This is 1 over delta x. Okay, so now this thing is, well, just for only once, let me write this. This is how we think about this. Now this is 0 over delta x. Okay, 0 over delta x is different than 0 over 0. Okay, remember in all our discussions about limits, we insisted that when in the limit something is going somewhere, it's never there. Okay, it's always getting closer to that. Okay, for several reasons, for geometric reasons also. But now here, that proves to be useful. Okay, so here, this means delta x is different than 0. Okay, so delta x goes to 0. So 0 divided by some number, that's a well-defined expression, that's 0. Okay, so you immediately write from here the result, but this part I'm writing just only once to see why there is no confusion. Okay, 0 divided by something is 0. Okay, limit of a constant is always that constant, whatever that constant is. Okay, so f prime is 0, okay, as expected. Okay, because we have to check these algebraic results with our geometric intuition. If they don't agree, either we change algebra or we change our intuition. Okay, so remember, after Einstein's calculations, since we couldn't change his calculations, we had to change our intuition about physics. So you do the same thing here. Okay, so this says that the slope is 0. What does it mean? It means you have a horizontal line. Okay, so that's what we are expecting. So far, so good. So let's write the equation of tangent line. Equation of tangent line. Okay, so you can immediately write the equation of the tangent line after you solve several problems, but I'll just repeat this. So this is y equals f prime x sub 0, x minus x sub 0, plus f of x sub 0. Okay, so now I substitute the values. Y is equal to this, f prime is 0, times, okay, so times x minus x sub 0, plus f of x sub 0 is always, f is always 1. Okay, so the equation is y equals 1. And we check if we were expecting this. This gives us this horizontal line. Well, that's what we were expecting. At any point, the curve itself, the line, is its own tangent. Geometrically, it's obvious. So we check that our algebraic manipulations give the same thing. Okay, so this is something which you always do. If the algebraic manipulation doesn't give you the same thing, then if it doesn't work in the simple example where you totally understand the answer, then you cannot trust this algebra in complicated cases where you don't know what the answer is. Okay, so that's why you check these trivial cases. Let's check one more trivial case. Well, the other trivial case, okay, let's check one more trivial case. Y equals x, in which case it's again a straight line. Let's check if it will again give a straight line. Then we'll do y equals x squared. And then we'll do something wild, y equals 1 over x. Okay, let's try these things. Okay, so 2 f of x is equal to x. Okay, so again, the graph is something like this. This is y equals f of x. Here is y-axis, here is x-axis. Again, at any point, x sub 0, we geometrically expect that the tangent line will be the line itself, because it's already a straight line. Okay, here the slope is 1. Okay, so let's make it, okay, I was going to put some constant there, but anyway, let's see if we will get y equals x as the tangent line, because here again we expect this same thing. The curve must be its own tangent. Okay, so we calculate f of x sub 0 at an arbitrary point, limit delta x goes to 0. I always suggest that here you write the general formula and then substitute it. Sometimes one is tempted to immediately from here pass to here, which is no problem, but if you realize that somewhere there is a mistake, when you go back and try to check where you made a mistake, it's easier if you do it this way. Then you check that you didn't make a mistake here, you go to the next step. So that's why I always write the obvious formula here and then do the substitution. Okay, so let's see. Delta x goes to 0. Okay, so this is f at this point. F at every point sees the point as it is. So this is x sub 0 plus delta x minus f of x sub 0 is x sub 0 minus x sub 0 divided by delta x. These cancel. So I have delta x over delta x. Delta x, here I write this just to remind myself. Okay, so this is not necessary. This is inside the definition. When delta x, limit of delta x goes to 0, means that delta x is different than 0. I'm just writing this to remind this to myself. In general, you don't write these things. So a non-zero number divided by a non-zero number, that makes sense. It is 1. Okay, so this is 1. Okay. Okay, next I write this equation. So equation of tangent line. Y equals f prime x sub 0, x minus x sub 0, plus f of x sub 0. Now I substitute the things that I know. Y equals, this is 1, times x minus x sub 0, plus this is x sub 0. So y equals x, as expected. Okay. So in these two totally trivial cases, our algebraic manipulations agree with our expectations. Okay, now let us do something curved and see what the tangent is. So let's do y equals x squared. Equals x squared. Okay, so now we know what the shape of this is again. So it's something like this. So y equals x squared. This is x. Let's take an arbitrary point again. We are doing this at the point x sub 0. So we are at this point. Now this point is x sub 0 square. Okay? It squares this. So we calculate the derivative. Let's see what the derivative will turn out to be. Okay, so f prime x sub 0 is equal to limit delta x goes to 0. Then we write the usual quotient. Sometimes this is called the Newton quotient, so that it's easier to refer to that. Okay, just an extra name. Okay, so Newton and Leibniz, well, Leibniz lived in Leipzig. Newton and Leibniz discovered these things at the same time. And before them, Isaac Barrow discovered these things, but he didn't develop these ideas. He generally explained this to other people. And even though Newton discovered this, he didn't use it because he was afraid people will criticize him. So when he wrote his masterpiece, Principia Mathematica, he doesn't use derivatives there. He proves everything geometrically. So later, when they were fighting with Leibniz about who discovered this, he brought these out. And for some reason, now it is called Newton's quotient, not Leibniz quotient. But to revenge that, the notation we are using, this notation is Newton's notation, but I'll show other notation, more convenient notation. Everybody uses Leibniz notation in derivatives. Okay, so let's go back to this. Let's substitute these numbers in. So this is limit delta x goes to 0. So this is square of this. Okay, so let's first be pedantic and write these things, delta x. Okay, so now limit delta x goes to 0. I take the square of this, 2x sub 0 delta x plus delta x square minus x square divided by delta x. These cancel. And you check that everything in the numerator is divisible by delta x. This is generally what you expect. Okay? If it doesn't come out like this, you either made a mistake in the calculations or the function doesn't have a derivative. Okay? The terms that don't involve delta x's in them cancel each other conveniently. Okay? So in Hollywood movies, this is said conveniently dead. The formula is conveniently dead because if that character lives on, there's no way to resolve the scenario to a happy ending. So the scenarist kills them. So here we kill these guys. Well, these guys kill each other conveniently. And you divide by delta x. We know that delta x is different than 0, so we can cancel. So what remains is 2x sub 0 plus 1 delta x. Okay, so now it's easy to see what happens when delta x goes to 0. This is 2x sub 0 for any point x sub 0. Okay, so let us write the equation of the tangent line. So this is y equals f prime x sub 0. It will be 2x sub 0 x minus x sub 0 plus f of x sub 0. Okay, so let's see what it is. This is 2x sub 0 x minus x sub 0 plus x sub 0 square. Okay, shall we simplify this? So this is y equals 2x sub 0 x, okay, and minus x sub 0 square. Okay, so at the point x sub 0, you put x sub 0 here. We have 2x sub 0 square minus x sub 0 square, so it will give you 1x sub 0 square, which is this point. Okay, so the line passes through this point with the correct slope. So this is the tangent line. Okay, so now let's do 1 over x, and I think, okay, so we also have square root of x. Okay, so let's check. f of x equals 1 over x. So let's do this for x positive. We know that there's also a branch on the negative side, but we'll check the derivative at only one point. So we know that the picture is something like this. X, y, so y equals 1 over x. So here, this point is 1, 1. Let's take an arbitrary point here. Okay, so x sub 0. So this point is x sub 0, 1 over x sub 0. So let's see how the algebra works. We want to go over the same calculation, the same routine. The only thing that will be different is after we put this substitution, we will start calculating the limit. And so far we had 3 examples. It was trivial. So let's see what we will get here. Okay, so f prime x sub 0 is equal to limit delta x goes to 0, f of x sub 0 plus delta x minus f of x sub 0 divided by delta x. Now we put in the formula for f. Delta x goes to 0, so this is 1 over x sub 0 plus delta x minus 1 over x sub 0 divided by delta x. Okay? So far, so good. So let's see if we can simplify this. Limit delta x goes to 0. Okay, I have 1 over delta x. Then here I have x sub 0 times x sub 0 plus delta x. So I multiply this by x sub 0, and I multiply this by this, x sub 0 minus delta x. Okay? You check, you note, so the responsibility now totally belongs to you. I continue. Okay, so again, there are 2 things which don't contain any delta x in them. If they stayed here, I would have 0 division. They are conveniently dead. I have this delta x canceling with this delta x. And I have this limit now. Limit delta x goes to 0. I have this minus, okay, minus, so let's say minus 1 times 1 over x sub 0 plus delta x. Okay? This is a rational function of delta x. I put delta x equals 0. I get a number. So that's the limit. Okay? If I didn't get a number, then I would try some other things. So you put delta x here. You get 1 over x sub 0 square, and you have minus 1. Minus 1 over x sub 0 square. Okay, so we got a negative slope. Does it fit with our expectation? If I have, wherever I choose this x sub 0, you see it's always like this. The slope is negative. Okay, so carry this over here. This is the negative slope. So at least the negativeness of the slope agrees with my expectation. Now the equation is easy. You just write the equation. Equation of so y equals f prime x sub 0, x minus x sub 0 plus f of x sub 0. Okay, so this is y equals minus 1 over x sub 0 square, x minus x sub 0 plus 1 over x sub 0. Okay, so it doesn't make much sense to simplify these. Okay, so this is the equation. Okay, so let's do one last thing as I prepared. Well, I say let's do y equals square root of x, so let's do square root of x. So that was 4, right? Okay, so 5 f of x is square root of x. Let's say x is positive. Well, actually, this is defined when x is also positive. Okay, but the graph of this is something like this. Okay, well, it doesn't go down, but it's something like this. Y, x, so this is y equals square root of x. So if you play with these things, you understand that since this goes like this on this side, if you if you take the negative square root, okay, square root of a number is plus or minus. Here I'm taking only the positive square root. But if you take the negative square root, it will continue like this. So the tangent line here, geometrically a tangent line exists and it is vertical. But algebra does not recognize vertical tangent lines because the slope is infinite. And it's not only plus infinite, because if you are approaching from this, you see the slope is negative here. The slope is becoming infinite. So in the limit, the slope is minus infinite. But in this case, the slope is positive. You are approaching here. In the limit, it is plus infinite. So the limit process doesn't agree there. Therefore, we agree that if there is a vertical tangent line, this kind of algebra will not see. Okay, so there you need to do some vector algebra, other things. Okay, as long as you understand what you are doing, you can recover the tangent curve there. Okay, but so far we are using this approach, which is the main technical tool. Let's check what the derivative is. Okay, so again, let's take an arbitrary point x sub 0. So this is the point x sub 0 square root x sub 0. F prime at x sub 0 should be given by this limit operation if the limit exists. F of x sub 0 plus delta x minus f of x sub 0 divided by delta x. And next step is just putting in the values. Then we'll start to think. So far we don't think at all. X sub 0 plus delta x minus x sub 0 divided by delta x. Okay, so now we start thinking. When we had something like this, we multiplied the numerator and denominator by the conjugate of this expression, which we don't totally understand as far as algebraic manipulations are concerned. Okay, so we decide to multiply this like this, x sub 0 plus delta x plus x sub 0 divided by x sub 0 plus delta x plus x sub 0. Okay, so at this point, while no one is looking, you check that when you put delta x equal to 0, the denominator will make sense. But it will make sense when x sub 0 is different than 0, okay? Because if this is 0 and this is also 0, you will have 0 in the denominator, okay? So you just keep this in mind. At least when when x sub 0 is different than 0, this will be convenient. You put delta x equals 0 and you get something nice here. The only thing is now, can I cancel this with something in the numerator? Okay, so we continue with that. So let's do this here. Limit delta x goes to 0. Okay, now when we multiply these things, we have x sub square of this is this, minus square of this is this, divided by delta x times x sub 0 plus delta x plus x sub 0. Okay, so now everything looks good because these are conveniently dead. These cancel. Now I have again this minus here. Okay, I put delta x equals 0. I get something meaningful. So the limit is minus 1 over 2, because now I have 2 of these, square root of x sub 0. But I notice that this will not make sense if x sub 0 is 0. So this is, I say, if x sub 0 is strictly positive. Okay? Eh? What? We have minus? Okay, so last year I didn't have a minus. I was wondering why this year I got this minus. Okay, so we don't have a minus. Okay. So the function is defined at this point at x equals 0, but the derivative is not defined at x equals 0. So the derivative makes sense when I get positive. X0 equals positive. Okay, so the equation of tangent line, let's finish it with this. Equation of tangent line. Y equals f prime x sub 0, x minus x sub 0 plus f of x sub 0. So I put this thing here, 2 square root x sub 0, x minus x sub 0, plus the value of f at x sub 0 is x sub 0. Okay? So if you want, you can simplify this with this one. Will simplify probably with this one, but okay, let's leave it here. Okay, so it looks like this thing is something trustable. So now let's test this at a case where we know the tangent line does not exist. Let's check if this method will recognize that the tangent line does not exist. Okay. Okay, so f of x is equal to absolute value of x. Okay. So remember the definition of this. The definition of this is x if x is greater than or equal to 0, minus x if x is less than or equal to 0. Here x equals 0, here or here doesn't matter because in both cases this will be 0. But in general, you have to be careful here, okay? When you say x equals 0 and this is 1, and x here you check this x equals 0, this is minus 1, then this is not a function, okay? But in this case, since they agree, I can put equal in both sides. Okay, when they look at the graph of this, the graph of this is like this. Okay, so this is y equals absolute value of x, y, x. So here I have y equals x. Here I have y equals minus x. In both cases, we calculated the derivative and the tangent line. This is a straight line. So at every point other than 0, I'm talking about a straight line, and the tangent line exists, and it is equal to itself. What happens at 0? Now we are just looking at the picture. So this guy says, use my tangent line, and so this will be tangent line at this point. But this says, no, I'm bringing a new tangent line. Use this line as tangent line. They don't agree here. If they don't agree, then we say they don't have a tangent at that point. Also, geometrically, what we expect from a tangent line without any calculation or without any scientific precision, tangent line must be the unique line that touches the curve at that point. Okay, but here, this line touches the curve at that point. Move this in any way you like. It touches the curve without intersecting it at any point. Okay, so there is no unique tangent line that will satisfy us. So we agree that this curve has no tangent line at x equals 0. Okay, so let's see if algebra will recognize it, okay? Because algebra does not look at the graph. There are only equations. And if algebra gives us a slope at x equals 0, then we'll just erase all of these things, start from the beginning, and try to implement something into the formula which will recognize that this doesn't have a slope at x equals 0. Okay, so let's check f prime at 0. Okay, now at any other x sub 0, we know what is happening. We calculated that. So the problem, the only question is if this technique will recognize what's happening at 0. So I start with 0 here. Limit delta x goes to 0 of 0 plus, okay, let me write 0 plus delta x. So I'm mimicking this one. So maybe I should just write f here. F of 0 plus delta x minus f of 0 divided by delta x. Okay, so let's not change our habit. That was our habit. We always write the formula here. And here we were writing x sub 0. Now our x sub 0 is a precise number, so I wrote it down. Now I put the formula. Delta x goes to 0. Okay, so this is 0 plus delta x is delta x, absolute value of delta x, minus 0 divided by delta x. Okay, so I want to check if this limit exists. But the value of absolute value changes depending on the sign of this. So I have to do two limits here. Okay, so we have two cases. Limit delta x goes to 0 from the right and limit delta x goes to 0 from the left. Okay. If the limit exists, these two limits will be the same, and conversely, if these two limits exist and are the same, then that's the limit. That's what we are checking. Now, when delta x is positive, absolute value of delta x is delta x. Okay, we are taking delta x to 0, so delta x is different than 0. I cancel, I get 1. When delta x is negative, its absolute value is minus delta x, so that I get a positive number, minus delta x divided by delta x. Again, delta x is different than 0, so I divide and get a meaningful thing. I get minus 1. Okay, so they don't agree. The right and left limits do not agree. So the limit does not exist. Okay? So our technique recognized that there is some ambiguity at the origin and said there is no slope. So when you translate it to our geometric language, algebra tells us that there is no tangent line at the origin. Okay, so this says, so this says that there is no tangent line at x equals 0. Okay. Okay, any questions so far? No questions. The same thing. You look very worried. Okay, so this thing, this idea will be used in some other cases also. So let me do one more example before we take a break about something like this. Okay, so here I have, okay, so this is x squared. So let's continue with the numbers today. So I define a function as x squared if, so let me, well, if x is less than or equal to 3, and say m x minus 3 plus k if x is larger than 3. Okay, so let's ask a few questions. So first, A, find k such that f is continuous at x equals 3. At any other point, you see if x is strictly less than 3, we have x squared, which is a polynomial. So f is continuous, it's a parabola, it's continuous everywhere on this side. If x is larger than 3, it's a straight line. Again, as far as algebra is concerned, it's a polynomial of degree 1. So it is continuous everywhere, no matter what m or k is. Okay. But if the two graphs don't touch each other, then it will not be continuous at x equals 3. Okay? So the value of, so for this thing, for continuity at x equals 3, we need to apply the definition. Okay, so to apply the definition in this case. Okay, because if we said, is it continuous at x equals 0, you look at the definition around x equals 0, it is defined like this, so you don't have to apply anything. You just use our knowledge that polynomials are continuous. Okay, so you don't do anything. But here at x equals 0, we have two different formulas for the function. So we have to check if those two formulas agree. How do we check this? We check if limit x goes to 0, 3, x goes to 3 of f of x is equal to f of 3. Okay, so f of 3 is 9. I know this from the definition. Okay, so this is what I have to check. But this limit is equal to two limits. Limit as x goes to 3 from the right and limit as x goes to 3 from the left. I do this. Normally, you don't do such things. If there's one big formula, you just check. On the right-hand side, I have a different formula. On the left-hand side, I have a different formula. But here, this is limit. This is easy. So let me do this one on the left. So this is f of x is equal to limit x goes to 3 from x squared. Well, this is a polynomial, so you just put in the value. This is 9. So on this part, it is OK. So for this thing, I have limit x goes to 3 from the right of f of x. The formula when x is to the right of 3 is this. So I write limit x goes to 3 from the right of mx minus 3 plus k. So you see, you put, this is now a polynomial once you put in the formula. Okay, so with polynomials, you just plug in the value to get the limit. So here, when you put x equals 3, you'll get k. For the limit to exist, first of all, this must be equal to this. And if they are equal, that's going to be equal to this number, so we are done. So k is 9 for f to be continuous at x equals 3. Okay, so let's stop here, and next time we'll continue from here, writing now that k equals 3, find m. K is 9. Okay. Now that k is 9, find m such that f prime 3 exists. Okay, so that's what we will do after the break.